Okay, so um, here I'm going to explain how to use Sage to compute things about the determinant. So first of all, we've got a random matrix command here that creates a 4x4 random matrix with coefficients in the ring of integers. So you do have to include the ring that your matrices have entries in. Here, ZZ is integers. If you use QQ, that's for the rational numbers. And I think RR is for the real numbers. But anyway, and then here's another matrix B, just a random 4x4 matrix. And here's what A and B are when I ran this at this moment. You'll probably get different matrices for A and B because these are just randomly generated matrices. Okay, so these are 4x4 matrices, so they're square matrices because I want to compute the determinant, and you can only compute the determinant of a square matrix. Okay, and then one thing I want to show via Sage is that if I compute the product, well, first of all, let me compute the product, A times B, so we get this. If you just type in plain AB, that's going to give you an error. So you have to type A asterisk B to get the product. And okay, so this is the product of these two matrices A and B. So it's again another 4x4 matrix. And then we take the determinant. So the command there is dot determinant of the matrix you're trying to take the determinant of. And so okay, this product here has some huge determinant, and then I take the determinant of A and the determinant of B and multiply them, and I get the same answer. So this is illustrating this theorem that the determinant of A times B is equal to the determinant of A times the determinant of B. And again, when you run this program yourself, you'll get different values for this determinants because your matrices will be different. Okay, then one thing that's not true is that the determinant of A plus B is not the same as the determinant of A plus the determinant of B. And then here I just did a calculation that shows that the first line 30/20 is the determinant of A plus B. The second line is the determinant of A plus the determinant of B. And they're not equal. Okay. All right, so then I want to talk about elementary matrices. So if you want to find out exactly how Sage is using this, or the notation, I should say, or the syntax for the elementary matrix command in Sage, you type in elementary matrix with a question mark, and that will bring up the help file for how to use the elementary matrix command. And it's a little bit confusing at first, but let me try to highlight what's important. So here's the first command, or one thing that's important, is that if you want to find or get the elementary matrix that swaps rows I and J, here's the syntax or notation for it. Now, one important point is that in Sage, numbering starts with 0. So what I normally in my lectures and everyone else calls row 1, Sage refers to as row 0. Okay, and I'll illustrate that in a few moments. But okay, then so basically, if you want to swap rows 2 and 3 in your matrix, you would still write row 1 here, but the I would be 1, and the J would be 2. That will swap what I call, and the book calls, rows 2 and 3. You just have to subtract the numbers by 1, because in Sage, counting starts at 0. Counting the rows in the column starts at 0. That's kind of a typical thing in computer science. You start indexing at 0. Okay, then another elementary matrix is you take row I and scale it by a factor. So here is the syntax for that. And then finally, the third type of elementary matrix is where you replace row I by S times row J, is the way I like to say it. And again, yeah, I'll explain later about how to shift these indices down by 1. Okay, so blah, 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 blah. And here they've given some examples. So here's a matrix A that's a 4 by 10 matrix consisting of the numbers from 0 to 39. That's what range 40 is. And now the elementary matrix, this is the one that swaps what you have here for row 1 and row 2. Now, this would swap, they have here 1 and 3. So it's going to swap row 2 and 4. So let's, when you multiply on the left by E. So yeah, so first of all, to get the elementary matrix, you start with the identity matrix and then swap rows 2 and 4. And that's what they did here to get this, to get the elementary matrix. And then multiplying on the left by that elementary matrix to any matrix A of the appropriate size will swap rows 2 and 4. So here's our original matrix A. And when we multiply on the left by this elementary matrix E, we've swapped rows 2 and 4. So row 2 originally started with 10 to 19. Now it's row 4 is 10 to 19, and row 2 is 30 to 39. So hopefully this illustrates how you have to just shift the indexing by 1. Okay, then here's an illustration where the elementary matrix is multiplying the appropriate row by a factor of 10. And let's see, this is row 2 in Sage, so row 3 in what I would refer to it. And so indeed, row 3 of our matrix, original matrix, has been multiplied through by 10. And then here's another example of an elementary matrix. This is the one where you replace this row by 10 times the row listed here. So replace row 3 by 10 times row 2. Here's what they did to the identity matrix. They replaced row 3 by 10 times row 2. That's indeed here. Sorry, not replaced. Yes, replace row 3 by 10 times row 2 plus the original row 3. So that's why there's a 1 here. And then that's also what happened here. Okay. All right, so then, we don't have to worry about this. Okay, so that was just the help in Sage. All right, let's try to do that again. Here I'm going to cook up the elementary matrix that replaces row 2 by row 2 plus 4 times row 3. So here's what the elementary matrix is. And we start with the identity matrix, replace row 2 by adding to it 4 times row 3. Okay, and then here's what it does to a general matrix. So here's how to cook up a general matrix. You want to tell Sage that you want to introduce some variables, and this is the notation. I want to introduce variables A, B, C, D, E, F, G, all the way through I or J. And then I cook up a 3 by 3 matrix whose entries are A, B, C, D, all the way up to I. I didn't need J, but okay. And then if you want to just see the formula for what is the determinant of a 3 by 3 matrix, for a general 3 by 3 matrix, it's this. So it's a little bit complicated, but you can see that what they've done in this factorization down here is expansion by minors along the first column. So A times the determinant of this 2 by 2 matrix, that's EF HI, that's E times I minus F times H, and that's basically what they have here with once you distribute them negative sign. And then D times the matrix BC HI, so here's the D times the B times I minus C times H, and you have to put a negative sign on that D, so that's what you get eventually here. And then G times the BC EF matrix, and B times F minus C times F. Okay, anyway, now going back to our elementary matrix that basically replaces row 2 by adding to it 4 times row 3, that's what what E times A should be, and that's exactly what we see here, is that we've replaced row 2 by adding to it 4 times row 3. Row 3 is GHI, multiplying it by 4, you get 4G, 4H, 4I, and adding that to the original row 2 gets this. Okay. All right, and then let's now just get to a matrix with numbers. So let's take B to be a random 3 by 3 matrix with integer coefficients, and then E times B is this matrix here where we've replaced row 2. The original row 1 and row 3 are the same, and we replaced row 2 by adding to it 4 times row 3. And then what I want to illustrate here is that the determinant, how does the determinant of E times B and the determinant of B compare? Well, when the elementary matrix comes from the operation where you replace the row by adding to it another multiple of another row, the determinant does not change. And so here we see 483 and 483. Now let's consider an elementary matrix where you interchange 2 rows or swap 2 rows. This is the notation for swapping row, the 0 turns into 1, the 2 turns into a 3. So swapping row 1 and 3, here's what happens to the identity matrix when I swap rows 1 and 3, and this is the associated elementary matrix then. And then the determinant of F times B is affected by a negative sign. So it's the original determinant of B, but it changes by a negative sign, which is one thing we learned in lecture, or stated in lecture. Okay, and then finally the third type of elementary matrix is you replace a row by multiplying through it by a factor. Here I've just chosen the factor 5, and so the associated elementary matrix is you start with the identity matrix, multiply row 3, again this row 3 because the indexing is shifted by 1. So this 2 becomes a 3. So row 3 of the identity matrix, you just multiply through by 5 to get this, and then here's again what B was, and then when I compute G times B, I take the original B and multiply the third row through by 5, so minus 2 turned into a negative 10, 3 turned into a 15, and so forth. And then the determinant of that matrix is this, whereas 5 times the determinant of B is exactly the same thing. So this is illustrating the fact that if you multiply or do the elementary row operation corresponding to multiplying through a row by a certain scalar, the determinant gets multiplied by that scalar. And that's pretty clear from the expansion along minors definition of determinant.